Assalamualaikum warahmatullahi wabarakatuh. Now we came to the second part of chapter 3, Dynamics PHY013. Okay, so we will discuss about a physical quantity called linear momentum. Okay, the first we go to the definition. Mathematically, linear momentum is the product of mass times the velocity. Product here means multiplication of mass and velocity. Velocity is a vector quantity, so mass times velocity will produce a new vector quantity called linear momentum. So from the formula of linear momentum, P equal to m mass times velocity, we have the SI unit for momentum, that is kilogram meter per second. And linear momentum has a relation to the net force that we have discussed in Newton's second law of motion. Okay, so this is the equation for linear momentum. P equal to m times v. Note that on the left and on the right side of the equation, the sign is the same. This means the direction of vector linear momentum is the same as the direction of vector velocity. And for the relation between the net force and linear momentum, the net force F net equal to ma. It is also defined as delta P over delta T, that is the rate of change in momentum. Okay, now we come to one of the important principles in physics, that is the principle of conservation of linear momentum. This principle states that when the net external force on a system is zero, that is F net, the total momentum of the system is constant. Okay, so the statement there we can write in equation form as shown here. F net equal to delta P over delta T equal to 0. Okay, so if delta P over delta T equal to 0, this means delta P, that is the change in momentum, is 0. There is no change. So this means total linear momentum of the system is constant, or in equation form we can write it the initial total linear momentum is the same as the final total linear momentum of the system. Okay, now we go to the application of the principle of conservation of linear momentum. Okay, the first application is elastic collision. Okay, so what are the characteristics of an elastic collision? The first characteristic is the linear momentum is conserved. Okay, remember what we have discussed in the previous slide. The total initial linear momentum is the same as the total final linear momentum. Okay, here is the equation for the total initial linear momentum, that is m1 u1 plus m2 u2, and for the total final linear momentum m1 v1 and m2 v2. Please note that u is for the initial velocity before the collision, and v is the final velocity of the objects after the collision. The second characteristics of elastic collision is kinetic energy of the system is conserved. This means the total initial kinetic energy is the same as the total final kinetic energy. Okay, so the total initial kinetic energy half m1 u1 square plus half m2 u2 square is equal to the total final kinetic energy, that is half m1 v1 square plus half m2 v2 square. Okay, that is the second characteristics. For the third one, the colliding objects, the objects involved in an elastic collision are separated after the collision. Now let us look at an example of an elastic collision. A proton of mass 1.66 times 10 to the power of minus 27 kilograms moves with a velocity of 1.25 times 10 to the power of 6 meter per second before it collides head-on with a helium atom at rest. The helium atom has a mass of 6.64 times 10 to the power of minus 27 kilograms and recoils with a speed of 5 times 10 to the power of 5 meter per second. If the collision is elastic, calculate the final speed of the proton. Okay, since the collision is elastic, okay, so we apply the principle of conservation of linear momentum. Okay, so the momentum before impact is equal to the momentum after impact. Okay, so initially the proton has an initial velocity, whereas for the helium it is at rest. So here UHI is 0. Okay, so we substitute the values for the total momentum before the impact, and we have the information on the velocity of helium after the collision. Okay, that is 5 times 5, 10 to the power of 5 meter per second. And we want to determine the final velocity of the proton. Okay, VPF then. Okay, so we substitute the values for the total final linear momentum. Okay, so calculating, we have VPF is negative 7.5 times 10 to the power of 5 meter per second. Okay, now we look at the second application of principle of conservation of linear momentum. We call this inelastic collision characteristics. Okay, we want to look at the characteristics. Okay, the first characteristics is linear momentum is conserved. Okay, so it is the same as the first type of collision, that is the elastic collision. So M1 U1 plus M2 U2 is equal to M1 V1 plus M2 V2. Okay, so the second characteristics, the kinetic energy is not conserved. Okay, here after the collision, the object will experience loss in energy. So we can deduce that the total initial kinetic energy is less than the total final kinetic energy. The third characteristics are the colliding objects stick together and move after the collision with the same velocity. Okay. Now we go to an example of inelastic collision. A 16-gram mass is moving in the positive x direction at 30 cm per second, while a 4-gram mass is moving in the negative x direction at 50 centimeter per second. They collide head-on and stick together. Calculate their velocity and direction of movement after the collision. Okay, so let's look at the solution here. Let the 16-gram mass be M1 and the 4-gram mass be M2. By taking the positive x direction to be positive, U1 is 30 centimeter per second and U2 is negative 50 centimeter per second. From the law of conservation of linear momentum, okay, momentum before impact is equal to momentum after impact. So momentum before impact, both objects are moving. Okay, so we have M1 U1 and M2 V2. And if we look at the momentum after impact, the object stick together and move with the same velocity. So the momentum after impact will be M1 plus M2 times V. Here, after the impact, there is only one velocity for both of M1 and M2. Okay, substituting all the values, we get V, that is the final velocity of the objects after the impact is 0.14 meter per second. Okay, note that V is positive here. Okay, and if we check our initial assumption earlier, that is by taking the positive x direction to be positive. So if V is positive, this means both masses move in the positive direction after the impact. Okay. Now we go to the third application of principle of conservation of linear momentum, that is the phenomenon of explosion. The characteristics of an explosion, the first one is linear momentum is conserved, kinetic energy is not conserved, and the object will when an object exploded, it will turn into fragments, and these individual parts of the system will be separated. Okay, let us look at the diagram shown here. Okay, we will take an example of a firecracker. A firecracker placed in a stationary object will cause the object to explode. Before the explosion, the total system momentum is 0. Upon explosion, the object will break into a variety of fragments. The vector sum of the momenta of the individual fragments is 0. The total system momentum is the same before and after the explosion. Okay. Now let us look at an example for explosion. A 56.2 gram tennis ball is loaded into a 1.27 kilogram homemade cannon. The cannon is at rest when it is ignited. Immediately after the impulse of the explosion, a photogate timer measures the cannon to recoil backwards a distance of 6.1 centimeters in 0.0218 seconds. Determine the post-explosion speed of the cannon and the tennis ball. Okay, here we take an example of a tennis ball firing cannon. Okay, what happens after the ball is fired? Okay, so after the explosion, the cannon travels 6.1 centimeter at a constant speed in the 0.0218 seconds to the left. Okay, so here the object, the cannon travels at constant speed. Okay, so in order to calculate the velocity of the cannon, we use the formula v equal to d over t, where d is the distance and t is time. So we get v to be 280 centimeter per second to the left. Okay, please do not left out the information of the direction of the cannon. Okay, since v here is a vector, so when we state the value of v, we must also state the direction of the velocity. Initial speed of the cannon UC is 0 meter per second, and also the initial speed of the ball UB is also 0. So from the law of conservation of linear momentum, the momentum before explosion is equal to the momentum after the explosion. Okay, mcuc plus mbub equal to mcvc plus mbvb. So 0 here for the initial, but we have a value for momentum after the explosion. So by substituting all the values that we have, we can determine that vb, that is the velocity of the ball after the explosion, to be 63.2 meter per second to the right. Okay, that's all for our discussion on linear momentum. Thank you for your attention. This video concludes our discussion on chapter 3 of dynamics. Please go to MOOC PHY083 website for additional activities and assessment materials. Thank you very much.